So yeah, hello. So actually, this video is away from academic fluff. It's stripped away to focus on why it actually matters, or why the calculus matters in machine learning. So let's first say if you searched online, you will find two contradicting camps. Let's say camp A says that you don't need math, just import TensorFlow, whatever the machine learning library is, which is for camp A. Then the other one, that is camp B, says you cannot touch AI unless you solve multivariate integrals by hand and do mathematics and complex integrations and differentiations and do this dark type of magics. So yeah, we are going to find out, are these hieroglyphics are really important, or the just knowing what the market needs, or just an import, or let's make the AI do the AI for himself, or what, so on. So the honest truth, both are on the right spectrum, but you don't need calculus to run a code, but you desperately need calculus to fix the code when it breaks. Today we are going to look under the hood of the black box of machine learning, and we are going to see exactly where the calculus lives. Is it inside, outside, or on the action itself? So why is it an engine of intelligence? Specific steps we're going to know now. So let's do a visual metaphor. So let's make a mountain that is a little bit foggy on the top. So standing on the top of this mountain at night is going to be pitch black and foggy. Your goal is to get to the absolute bottom of the valley at the lowest point, because it represents the lowest error, yeah, in your model. So the landscape, or the function, the shape of the mountain is defined as a mathematical function in machine learning, is called the loss function, yeah. And there's steps. These steps to get up are called derivative. Okay, so when you derivate or do a derivative, okay, you can't see the bottom. You can only feel the ground under your feet. You feel which way is sloping, yeah, down or up, that you slope, and this is the derivative. Okay, so of course it has many other explanation, like if it tends to a limit, or has a minima or a maxima, but let's say just the slope for now. Okay, if it has a slope. Okay, so, and there's a walk, the steps itself, the algorithm itself, how we will walk. The step in and the direction of the slope is it repeats until the ground flattens out. The process called gradient descent. Okay, gradient descent. It's let's do it as this sign for now. Okay, called it's the inverse of the nebula. This is nebula. Okay, this is like, let's do it as, we call it partial or whatever, like delta. Okay, call it delta. Okay, this is the step. So we need three more important steps. So the delta, and before it the step, and before it the landscape itself, or as we have called it, the function. Okay, so calculus provides the compass. Is in the dark. Without it, the model is paralyzed. It doesn't have to know how to improve. It doesn't get to know how to improve. Okay, so where the calculus appears, it comes here. If people are familiar with this is like inputs, weights, and transfer function, as we have just called it, and an activation function, and the output is here, the input is here. This is a layer. So let's say this is layer 1. People sometimes call the input as layer 1, but we want to call this the input as I, output as O. And this is layer 1. This is the layer inside. When there is more than one layer, we can't see the layers and their action inside. So sometimes they call it hidden layers. Okay, it can be more than one layer. So this is the inputs for me. Okay, this is the inputs, like some data, digital data, can be analog, it can be whatever data, and this data is coming on a perceptron, and this perceptron is added to it a weight. Let's say like if w equal 0.5, so we're gonna multiply x1 by w, which is 0.5, getting us weight is equal to x1 dot 0.5. Okay, so this is the result of the w. Okay, times. Okay, and this is going to be the summation of all of these. As you see, it makes the sigma sum, which is the summation of all of these. So it's gonna be the sum of weight 1, weight 2, or let's say let's call it z1. Z1 is equal to x1 times 0.5, z2 plus z3 plus z4 is gonna be here. Okay, so let's say the result was 0.7, for instance. So now the activation function here defines if this value is going to meet our function or not. Like most of our functions, like say if it is resistance, for instance, resistance is a linear function by the volt and current. Yeah. For instance, the transistors like BGTs and MOSFETs and like other functions are, let's say, weather. They're not going to be that complicated, but it's going to be a complex one, a more than a first degree one, or just a simpler linear regression. Well, not gonna call it linear regression, but a linear model. So it's gonna be complex. It's not gonna be on the all of the steps as the other. So this function is like this is, it defines whether is it on the point, out of the point, or is it not of the video, not of the value. So let's say if x is equal to 0.5 and our transfer function here is called for instance, let's do unit step function. Unit step function is one of the simplest. It's like this unit step. It's unit step. Okay, just a unit of step, and this step is if it exceeds 1, if the x is more than 0, the value is gonna be 1. If it's less than 0, or in other words negative, it's gonna be 0, like that. So let's say it's 0.7 here, it's gonna become out as 1. If it's, let's say, 0. Let's say for instance if it was negative 0.2, it's gonna come out as 0. So why would they ever get out the output as 0 and 1? Maybe this function is a gate, like AND gate, an OR gate, XOR gate, NOR gate. All these gates are binary, so things with binary are usually with an output of 0 and 1. But if something that is analog, we're not gonna simply use this. We're gonna use things more complicated, things like sigmoid. For instance, sigmoid is drawn like this. It's a function that is like smooth on the axis, on the x axis, on the y axis here, and is infinite. Yeah, there is exponential functions, like the exponential functions does that. And so there are many different functions for the action itself. We add this a threshold just for making sure our model is on the highest efficiency. Like the output is not gonna come out from the first instance, so we add this to make as an expert we usually add this to make the function even faster. Yeah. So if we added this threshold closer to the actual value that was gonna be output, so we have made the function faster. So the loss function is the first thing we're going to talk about here. So to teach a machine, you firstly quantify the failure itself. Okay, so so after we have outputted this thing, we're supposed to know if this is actually correct or not. We don't even know. This is a type of learning, but it is called supervised learning. Okay, supervised learning. We don't know this output is correct or not, so we're going to know by using the a mathematical formula, or just a simple loss function. It's called the mean squared error, MSE. You usually find it on the top of your calculator and things like that. It states that MSE is equal to y predicted minus y actual. So we have an actual value that has been outputted, let's say like 1, and we know for an instance that the output of the first one is going to be 0. So yeah, we have to prevent that from happening and to try to perform another iteration to learn, we do the predicted, or we have known it's already gonna be 0, and minus the actual which has been outputted as a 1, and by that we do find the error. Okay, the error is going to be the difference of these square. This is a way for doing the learning, or doing the error. So we treat this function as a curved surface. We need to find the minimum point of the curve, like here. So the minimum point, this is the local minima. To find the local minima, which calculus tells that the minimum point of the slope is 0. Yeah, okay. We can do differentiation of this. Yeah, so after we differentiate this, we're gonna find the local minimum. Why we want the local minima? To actually find the best solution. Yeah, the closest solution to our result. So the second thing we have talked about the error, okay, or the step, or the function. Secondly, we're gonna talk about the gradient. The gradient is the neural network has thousands of knobs. Like you have always seen this structure of like that, doing people connecting some neurons that way, and the neurons connecting that way, and connecting to that, and that connecting to that, and that getting outputs like that. Yeah, so have you asked yourself what this is even? So this again, this is the input, okay, this is input I, and this is output O, and this is the hidden layer, okay, HL. Okay, so these knobs or weights, which are multiplied by these inputs, we need to turn all of them at once to reduce the error, which again we didn't find. Let's say if we outputted here a 0 and the output we know is a 1, so this is an error. Yeah, so we need to calculate this error to apply on the weights which are here to fix them. Okay, so we just don't use simple derivative or simple derivative. We use the gradient, which is with that sign, the delta. Is a vector. This is a vector of partial derivatives. We do this entire weight section. Yeah, this entire weight section. This one, entire weight section, as a vector. Yeah. This tells us how much the error will change, and we wiggle each specific weight just a tiny bit. That's why in AI we need GPUs, because GPUs, it does parallel programming. It does all these weights together. All these weights are done parallelly. So if we did do each of these weights, let's say if it has like 500 neurons or something, it's gonna be endless. It's gonna run like for weeks. We wanna finish fast, so we do all these together. Yeah, so that's why because even this is for the first iteration. There's a first and a second and a third iteration, just to make sure that the output is correct on the highest accuracy. So that's why we need GPUs, or the graphical cards. So that was one of the questions. Why do we even need a graphical card, a graphics card for doing AI? We don't think there's no even visuals or things like that. Yeah, so it's because we do parallel programming here. We need to do all of these all together in a vector. That's why the gradient here is used. So the delta L tells us, or delta error tells us how much the error will change if we wiggle a specific weight. If the gradient for a weight is positive, decreasing the weight reduces error. Yeah, if it reduces error, so like if we decrease the weight, the error decreases if the weight is positive. Yeah, and if the gradient is negative, increasing the weight, it reduces the error. It's the vice versa. Okay, so there's another method for so this method was called forward propagation. So we do this After we do that, we find some outputs, and these outputs, if they're correct, okay, they are correct. If they're not correct, we find the error using the mean square error and the other methods. There's some sum of squares and there's other methods, and we do the iteration again by changing the weights here. So there is also a method called backpropagation, where it states that instead of like how we know that the weight in the first layer affects error at the very end even, yeah. So it's done by chain rule. This is chain rule. It's something from mathematics called dz by dx, yeah, equal dz. This is d, huh? No partial. dz by dy dot dy by dz, yeah, dx here. So like see, it's dz here, this one, by dx here, this one, and you just spread out this dy there and here, like on top here and on the bottom here, yeah. So the backpropagation is just a chain rule applied over and over again without the output layer being in the input, yeah. It allows the network assign blame to specific neurons in the first error. So do I calculate this by hand? Now we come to the actual question. Do I do any of this by hand? There is two sides of it. We can say no and we can say yeah. So on a no side, in your day-to-day job as a machine learning engineer, you will almost never calculate any derivatives by hand on a whiteboard. Libraries like PyTorch, TensorFlow have autograd engines that calculate this calculus for you automatically, and even higher models. So we're talking about a linear model, a simple model. What if it was a greater one? Like it needs an expert to do, an expert systems or fuzzy neurons. So yeah, this was the no side. But on the yeah side, if you still need to know it, you need this intuition for debugging, yeah. Okay, so vanishing gradients, like if you don't understand the chain rule, you won't understand why deep networks stop learning, yeah, why gradients multiply by 0. And the learning rate, if you don't understand the slope metaphor, which we're talking about the differentiation, you don't know why setting your learning rate too high. This learning rate is usually called as alpha or y prime. It's too high. It makes your model even diverge. Like if let's say this is the model and this is the iterations. This is the model. On the first iteration, it's on a high error here, yeah. The error gets lower, then it just gets steady, yeah. This is, let's say this is always on alpha is equal to 1. The speed is 1. What if we did alpha equal to 0.5? 0.2, let's even to 0.2. It learns slowly. Learning slowly is not bad here. Learning slowly means it does more iterations. It does more and more iterations. That makes it go even steeper. Yeah, it gets to the accuracies of above 90%. Yeah, so that's something we want. Yeah, yeah, it will take more iterations. These iterations are called epochs. Yeah, these epochs are the iterations that we perform. Okay, so if you don't understand the slope metaphor, you don't know that. Yeah, a learning rate, let's say, you would think, yeah, a higher learning rate equals it would learn faster, we're gonna finish faster, and yeah, we're gonna finish no, but the problem is that it decides on each step what weight to change and how and the entire vector, and this is on a simple model. We have token unsupervised or reinforced or any other model that would even require different methods of understanding. And yeah, the optimizer has a choice. Why is the Adam and SGD model better? Why should I even use any of these? The answer lies in how to utilize the gradient calculus and navigate the way. So if you want to master the necessary calculus for machine learning without getting a math degree, follow these steps. Master derivative for basic functions is going to be focused purely on derivatives. Understand something called the power rule. Yeah, the power rule. So the power rule, which is d by dx for x power n equal to n x n power x power n minus 1. Okay, so understand the derivative of e power x and len x used in the activation functions, and the goal is to understand the derivative that is just the rate of change, which I have to call the alpha, or the sensitivity. Yeah, sometimes called like that. The symbol of it is usually called as partial fraction, partial derivative of f of by partial x. So understand how change on one weight affects the error. Yeah, this is the other. So the first thing is the power rule, second thing is the partial derivative, third thing is the chain rule we just talked about. If y equal to f of u and u is equal to g of x, so we want to find dy by dx. Yeah, so we just did it from some minutes to be on this way. Okay, so yeah, it visualizes our signal. Our signal propagates through the layers of network. Yeah, so now visualize the gradient descent. This is the fourth step, the gradient descent. Don't just look at the math, look at the 3D plots. You'll understand even more from the 3D plots. Understand the convexity. Like this is the convexity, like then there's like that, and there's the function is going to doing like that, a bell shape, a bowl shape. So yeah, from here we understand that this is the minima. If the minima of your function was like here, it's not even the correct way. Yeah, so we can just use our expert systems, our expert knowledge to realize, yeah, this is the minima here from our shape. And then on convexity, many peaks and valleys, like this is not the absolute minima. What if it was on this shape, like say it was like that? So if the model got it like here, it's not the correct one. This is the right one, and this is the right maxima, not this one. This is the local maxima, and this is the global maxima, and like that. So yeah, this is the fourth thing, and the fifth thing is something called the micrograd, or the ultimate test. Don't use PyTorch. Write a tiny script in Python that creates the gradient of the simple function, like f of x is equal to x squared plus 3y. This updates the both of x and y and minimizes both. Yeah, so this bridges the gap between the math symbol of the delta and the code optimizer yeah, dot step. Sorry for what I'll just remove it. Okay, so yeah, okay, so that was what we were talking about, and that was all that we needed, but we can go again with it. So the calculus and machine learning is very important for us to understand, but as someone who works daily, you would usually need the library. So I'm usually with the part that says, if you are going to develop these machine models and learning models, so stick up with B. The people who learn these things, they have bright futures, bright minds, and it's something that's trending now. Okay, and it ran for a long time. It's replacing things, and it's getting our lives better. So it would always be needed to understand and learn. If you don't need any of these, you have a specific work, yeah, so you learn a library or a specific knowledge, and stick with the part of A. So this was on a simple supervised model. We have expressed how we do calculation and how the output is come, and here we find the local. We don't want to find the local minima, we want to find the global the global minima. Yeah, and this is the optimal. This is a linear function. They call this linear regression. We find from here this is what can be our function, activation function. So we need to understand the things here. So like say if the input was here, some of these dots were here and some of the outputs were here, so this line would converge to here to have something called the linear regression, to be on the mean of these values to be the most accurate between them. So it's usually between all of these points or results. Yeah, and this was the sigmoid function. This sigmoid function usually is represented by sigma. It's called sigmoid function, and it has this value. It's like 1/1 plus e power negative z alpha, sometimes x or whatever you name it. Okay, so yeah, so that was the difference. If you can, if you loved what I said, this is, so it's the better way for you to learn the mathematics of it, to learn the way it goes. It's lovely, it's simple, it's not like the other branches of mathematics. It's more related to computers, so it's more fun. Yes, but if you would get my honest response for the job market and what I have seen from my friends, and from the people on the job market, I would recommend that you learn a specific skill like library and tools, more than more than learning the mathematics and the calculus behind things. I hope you like this video, and please subscribe and like, and I would love to hear your questions, and thank you.